Properties of context-free language. Um, we Just to give you an idea, we have been looking for context-free languages, and the question, and we said context-free language will be driven from grammar-free language, and we set up a state diagram, and the state diagram which we use will provide approval that this expression belong to a context-free language or not. In this short lecture, we will describe what other properties for context-free language. We also recommend you that this lecture is available over podcast, and we if you don't have internet access, you can stop the video, or you don't have enough internet bandwidth, you can stop the video, download the podcast, and from that point you should be able to follow.
This video is subject to copyright. To maximize the use of this session, please connect a headphone and mic if you can. Stay in a quiet place. Adjust the sound of your computer. Close all other programs running on your computer. The instructor will direct you to open any other required program to use. Close chat programs in social media such as Facebook, Twitters, Messengers, WhatsApp, etc. Maximize your screen to see the four corners on this slide on your screen.
The very first property we'll be looking for its union. So we have to understand that context-free grammar or context-free languages, these are a set of words or expressions which can be defined by a canonical form, or it can be defined as illustration as sets. And both set forms will have some properties. So, and also there is some what we can say ordered couples or ordered tuples. So there are specific orders, they will come to it. So the very first one will be the union. So what are we saying here is, if I have two context-free languages, will the union of them will be context-free language. So the context-free language, the union of two different context-free language is an actual, it will result into a context-free language. And to find out the example here, I will look at an example here where I have a language defined as a to the power n, p to the power n. And the grammar of this language will be s will lead to as1, b, or lambda, or the null. And the other language will be w and w to the power r, which basically I have a word and I can repeat this word so many times. And this language can be defined as a, s to s, where s or b, s to b, and lambda. So the question is, if I have both grammars and both languages, will this produce the union? Will be yes or no. So the union of them means this one will be repeated or the second one will be repeated. So the union of both shall produce a language, and the union can be defined as s will lead to s1 or s2. So in this case, this is a simple example. If I move to slide 6, I would say that if I have language L1, L2, if I have grammars G1, G2, if I have starting value S1, S2, the language union the language will produce a new language, and S will be the new starting, which could be S1 or S2. So this is the additional production I have. So this is the way to construct a union of two language. What other properties of union could happen? The second property of union will be what we'll see in slide number 7. In 7, we discuss concatenation. Concatenation means if I have a term language L1 and L2, the concatenation is basically to have L1, L2. Concatenation comes from chain, which means I chain the language. So now the symbols will increase. So if I have a language L1 and the language L2, the concatenation of them, L1, L2, or L2, L1, which is the other concatenation, both of them will be a context-free language. So for example, here I have the same language, which is a to the power n, b to the power n, which basically a, s1, b, or lambda, and I have omega to the power r, or w to the power r, where s2 will be a s2a, or b s2b, and null or empty. So I have here the symbols are a and b, the starting symbol is s2, and I can keep going as many as I can as a, b, and b, b. Now you look at this is omega r, which is both of them are similar. So the concatenation of these two will lead to an bn with the set a omega r. So this resultant language here will lead to be a context-free grammar. So in general, if I have a language L1, L2, if I have a context-free grammar G1, G2, if I have the variable S1, S2, so the concatenation L1, L2, and the new starting value S, it will lead to S, the extra production will be S equal to S1, S2. So this kind of concatenation will result into language-free grammar. Moving to slide number 10, I want to talk about the star operation. Remember, the star operation is actual replication of the language, or you repeat the actual symbol. So if L is a context-free grammar, the L star is also a context-free language. So if L is a context-free language, L star is a context-free language. If I want to look at it as example in slide 11, I have L equal to an bn. The grammar S is as b lambda. The star operation will be an bn. And if you understand the star, you can basically replicate or repeat this particular set all over to the right hand side. So the new production will be S1 will lead to S1 and lambda. And from the previous example, when we talk about concatenation, the star here will define that's unlimited number of concatenation. So basically a concatenation will produce a context-free language. I will move to slide 12. So in general, for context-free language L with context-free grammar G and the startable variable S, the star operation over L will produce, when you have a new variable S1, for example, and then you have the additional production, how you produce the L star. We always remember to have the empty or the lambda. At this point, we spoke about how or what is the characteristics or what is a resultant of manipulating languages. So if we have two languages, how we get the other language. Now, the second part, which is starting on slide number 13, we talk about the negative properties of context-free languages, which basically the properties which can lead into issues. So for example, intersection. So if I have a context-free language which will intersect with another context-free language, it is not necessarily a context-free language. So if you remember in 2 lectures ago, when we describe how to drive a language to be a context-free language and how to generate the right rule. So for example here, if I have on slide 15, if I have the grammar, I have a language A, B, C to the power n and m, as you see it here, which basically a star or a concatenations. L2 will be an, bm, and cm. So the context-free language here and the production rule will give me the starting sample S, which will lead to A and C, and then A will be A capital B and lambda. C will be produced as C and then C or lambda. Then the context-free language will be AB, then A and lambda, and B, C and lambda. If you look at A intersecting L2, this will lead to AN, BN, CN. AN, BN, CN is not a context-free language under this production symbol. So I would leave this as a proof. So if you can prove that this language L1, L2, AN, BN, CN is not a context-free language. The following characteristics on or properties on section 30, on slide 16 is the complement. So a context-free language is not closed form under complement. So if I have L as a context-free language, L bar not necessarily a context-free language. So if I look at L1 on slide 17, I have an example here where L1 A to the power N, P to the power N, and C to the power M, while L2 will be A to the power N, B to the power M, L to the power M. So I have both languages. So if I'm not concerned with, we discussed before the production rules here. So if I want to look at the complement of these two languages, so it will be L1 complement union L2 complement and all complement. This will lead to L1 intersect L2, and L1 intersect L2 from previous properties we know it is not a context-free language. So basically the complement of a language is not a context-free language. Somebody will say, so why do you prove it in this way? I would just tell you, like, if you prove it in one case from the proven by induction that is not a context-free language, you have to stop. So to summarize here, we talked about the intersection and the complement are not context-free language, while we talked about a context-free language will carry if we have a union, if we have a star, or we have concatenation. And the star, it's unlimited number of concatenation. Now we come to the slide 18 and we want to merge the context-free language and the regular language. So the intersection of on slide 19, I'm just skipping the slide, so if somebody on the podcast, they can follow on the PowerPoints or the PDF file. The intersection of a context-free language and the regular language is a context-free language, because context-free language, if I dominate a regular language, it will be a context-free language. So if L is a context-free language and L2 is a regular language, the intersection of both is a context-free language. So I would like to move to the proof in 20. So I will say I will have a machine for M1 and a machine for M2. One is the determined and one is non-determined machines. So the one for L1 is a context-free. The one is L2 is a context-free. If I want to construct the one for L1 and L2, so this machine M will simulate in parallel M1 and M2. So because if you move to the next slide, which basically 21, you are basically having a machine which simulate M1 and to the right hand side machine which simulate M2. So the intersection will be a machine which simulate all the transitions of N1 and N2. So in this case, the machine itself, so here I have the transitions, here I have the initial states, I have the final states, and from them I can prove that this is our context-free language. So let's give another example here. So I will have L1 will be W1, W2, where the length of W1 equal length of W2, and W1 belong to AB and W2 belong to CD. So basically I want to create a similar length language. So the M will have A and lambda to 1, and then B and lambda to 1, and then C 1 and 2 lambda, D 1 and lambda, and then I can here produce the state diagram. So for the regular language, here is the state diagram. For the context-free language, here is the state diagrams, or the automaton for the context-free language. So in general, if M1 simulate in parallel M2 and M1 and M2, and if M1 accepts string W, if and only if M2 accepts string W and M2 accepts string W, so the intersection of this language will be L language 1, the intersection of language 2, and if M is context-free, so the intersection of both will lead to context-free, then L1 intersection L2 is context-free. So in the following section, which start on slide 30, we will speak about the application of regular closures. So the intersection of a context-free language and the regular free language and the regular language is a context-free language. This is what we have been able to discuss before. So if L1 is the context-free language and L2 is the regular language, the regular closure or the intersection is also a context-free language. So an application here is prove that L1 AN BM, where n less than not equal to 100 and n greater than 0, is a context-free language. So we know that AN BN, where n less greater than is a context-free language, and we know also that LAN A100 and B100 is a regular language. So what we want to say here is L1 complement will be the A plus B star minus A100 and B100. So what I want to say here is if I have a context-free language and I remove a term out of it, will the resultant be a context-free language? And the answer here is yes. So if I have a context-free language and I remove a term from it, it will still be a regular closure and it will continue to be a context-free language. Another application of the regular closure is prove that omega is NA equal NB equal NC is not a context-free language. So if L equal W NA equal NB equal NC is a context-free language, then L will intersect with the closure AN B A star B star C star, and the intersection of both will end up to be a context-free language here, which is AN BN CN. So a context-free language will intersect with regular language, and this will lead a context-free language. So if L is a context-free language, then context-free language intersect with regular language equal to a context-free language, which is basically impossible. So in this way, L is not a context-free language. So in this property discussions, we discussed few things. One is the impact on context-free language from intersection, from union, the difference between regular language and context-free language. And if you have any questions, please put them in the comment below or email them to me. Looking forward to see you again in the next lecture, and have a nice day.